Now, next data structure is heaps. Okay, so before talking about anything, let me make sure that this heap has nothing to do with the heap in the memory structure. Okay, in the memory structure, we have a stack and heaps, but accidentally we have the same name. Okay, don't get confused. Okay, let's talk about max heap. Actually, we don't have just a heap. Okay, so usually we use max heap or min heap. Okay, then what is a max heap? So before talking about it, let's talk about max tree. A max tree is a tree in which key value of each node is no smaller than those of children. For example, in this figure, 14 is larger than 12 and 7, and 12 is larger than 10 and 8. 7 is larger than 6. Okay, so the parent node is larger than its children. Okay, that's max tree, which means the root node is the maximum number, right? Because root node is larger than the children's, and the children, these two children are larger than their children, etc. So root node is the maximum number. Okay. So in the second graph, 9 is larger than 6 and 3, and 6 is larger than 5, and 30 is larger than 12. So all of them are max tree. Okay, then what is a max heap? Max heap is a complete max tree. Okay, so it should be complete binary tree, and it should be max tree. So the left one is a complete binary tree and it is a max tree, so it is max heap. And what about the second one? This one is also a max tree and complete binary tree, right? Okay, then the third one, okay, this one is also a complete binary tree. So these are examples of max heap. And as I said, it has nothing to do with the heap in the memory space. And the min heap is exactly the opposite of max heap. Okay, so let's talk about the min tree first. Min tree is a tree in which key value of each node is no larger than those of children. So in this example, 2 is smaller than 7 and 4. Okay, 7 is smaller than 10 and 8, and 4 is smaller than 6. Okay, in the second graph, 10 is smaller than 20 and 83, and 20 is smaller than 50, and 11 is smaller than 21. So these are min trees, and min heap is a complete min tree. So these are complete binary trees, and these are min trees, so these are examples of a min heap. Okay, so min heap is exactly the opposite of max heap, so without loss of any generality, we will just talk about max heap. Okay, so if you need a min heap, then you can figure out what to do if you understand the max heap completely. Okay. Then why are we talking about max heap? Okay. So max heap or min heap. These are efficient for extraction of the largest or smallest element, because if it is max heap all the time, the largest element is at the root node. Okay, and for insertion of new element is efficient. Okay, so we'll talk about these insertion function and deletion functions. And it is actually a compromise of sorted and unsorted structures. Okay, so if we have a sorted data structure, like an array or a linked list, okay, whatever, we have a sorted structure, then it is very efficient in extraction of largest element. Okay, so we know where is the largest one. So if it is sorted in an ascending order, then the last one is the largest one and the first one is the smallest one. Okay, so we can find it so easily. But it's not efficient when we insert a new node, new element, because this one is sorted, and then when we add one new node, then there is exact locations. Okay, so we have to find out where to put it. Okay, there is only one place to put it. Okay, and so that's efficient to extract largest, but not efficient in insertions. And how about unsorted structures? Okay, so we have an array or a linked list. And if we want to find the largest element, then it's not that simple. Okay, so we have to compare all of them. Okay, this is not sorted. Then we have to check all the elements to find out the largest element. So it's not efficient compared to the sorted structure, right? But unsorted structure is really efficient in insertion. So this one is not sorted, so nobody cares. So when we insert a new node, put it anywhere you want. Okay, it doesn't matter because it's not sorted anyway. Okay, so finding the largest element is not that simple, but insertion is really simple. Okay, and the max heap is in the middle of these two. It is between these two sorted structure and unsorted structure. Okay, think about this one. When we find the largest one, that's simple, easy, because the root node is the largest one if it is the max heap. Okay, and when we add new element, then anyway, this is not really sorted structure, so we can put it in a max heap, and the only constraint is that the parent node should be larger than the children's. Okay, the children's element. Okay, that's the only constraint. So when we add the new element, then we can check only that. So it's much more efficient than the sorted structure to insert. Okay, so we'll talk about all this extraction and insertion. Okay. Now, where can we use this max heap? Okay, so basically, we can use max heap for priority queue. To implement priority queue, we can use max heap. Okay, do you remember what priority queue was? So in chapter 3, when we talked about the queue, at the end of the chapter, we talked about the priority queue. Priority queue is a queue which deletes the element with the highest priority. Okay, so something like emergency room. Okay, if it is not an emergency room, then first in will be first served. Okay, but if it is an emergency room, then first in might be served later if you have more emergent case. Okay, as I said before, if you have a tiny little problem with your finger, okay, so you got in to the emergency room, but later someone with a big problem like a heart attack, and he comes into the emergency room, then who should be served first? Obviously, he should be served first because his priority is higher than your tiny little finger. Okay, so in that case, when we use a queue, when we add a new element into the queue, then we put a priority there. Okay, and then we don't have to sort the elements in the queue, but we should know which one is more urgent, which one has higher priority. Okay, so for that, max heap is the best data structure. Okay, and heap is an effective way to implement priority queue, and we can check the computational complexity. Okay, so let's say we have an unordered array, an unordered linked list, and sorted array and sorted linked list. So basically, unordered array and linked list, they have the same kind of computational complexity in a big O notation. Okay, so when we insert in an unordered array, then it's just constant. Okay, and then when we insert something into unordered linked list, it's just constant. Okay, and when we delete, we have to find where it is. So it takes n. Okay, so it is a linear time. Okay, what about the sorted array? Sorted array and sorted linked list, whenever we add a new element, then we need n in a big O notation because we have to find out where to put it. So basically, in the unordered list, we have to find the location to delete. But in the sorted array or sorted linked list, we have to find out the place when we insert. Okay, but when we delete, we know where it is, right? The largest one is the first element. Okay, so it's just constant. And max heap is kind of compromise between these two extreme cases. So when we insert, we need log n, and when we delete, we need log n. Okay, so it's better for the unordered array or linked list for deletion. Okay, and max heap is better than the sorted array or linked list for insertion. Okay, here is an abstract data type for a max heap. As an object, we can have a complete binary tree of n elements organized so that the value in each node is at least as large as those in each child. So basically, we have a complete binary tree and the max tree. Okay, and as an operation, we have a couple of functions. First one, create. Okay, so it's just basic operations. We can make an empty heap. Okay, and second, we want to check if it is full. Okay, and then next one is insert operations. So we want to insert new item into the max heap. Okay, and then result should be the max heap too. And we can check if it is empty, and we can delete one element from the heap. So if it is a kind of C++ implementations, then we don't have to pass this heap as a parameter, okay? Because it is a class member, so we know which heap we are talking about. So we don't have to pass this heap. So we talked about a couple of operations, but basically the other operations are really simple, okay? So checking if it is empty or full, it's just simple. We don't have to talk about those operations. And there are two important operations, insert and delete. So basically this is what we do, when we implement something with data structures. These data structures are taking care of adding new data elements, okay, or deleting one of them, okay. So in the stack, what we did was a push and pop, and with the queue, what we did was add or delete, okay. So with the other data structures, so main operations are just insert and delete, okay. These two operations are kind of the core operation with pretty much every data structures, okay. And then here is a problem. When we add or delete, we have to preserve the condition of max heap, okay. So there are two conditions. It should be a complete tree, okay. And then the second one is that it should be a max tree, okay. So when we add a new element, after insertion, still it should be a max heap. And when we delete, after deletions, it should be a max heap with these two constraints, okay. So from next slide, we will talk about insertion operation and delete operations, preserving these conditions.